Hey there, Applied Pre-Cal. We are moving on to interpreting graphs of linear functions today. What I need you to be able to do by the end of your practice on this lesson is I can give you a graph and you should be able to tell me what the rate of change is just by seeing the picture. Now what we've done so far is I've given you either a table of values or some points that were valuable. I'm not going to do that anymore. I'm just going to give you a picture. And I want you to be able to interpret that picture into a linear function. We're going to start by finding things like the rate of change, but then I'll start asking you to find the equation of a line and move forward with that as well. So let's start with finding the rate of change. Okay, so I just got that down there. What is the rate of temperature change in both locations? Well, it would help if I gave you a picture to work with. I'll explain it and then we'll get an image down. I'm going to give you a graph of two different locations. Doesn't really matter where they are, but they're going to be having a change in temperature. So it's like right now, if you step outside, it's the spring. So the temperature is getting warmer, but that's not necessarily always true, right? If you step out at say 9 p.m., as time moves forward, you're going to be experiencing the temperature getting cooler because it's getting darker, it's getting later on into the night. If I had you step out at say, 11 a.m., well, by the time it's 1 p.m., it's going to be pretty warm because the sun's been out for a while, it's warming everything up. Ta-da! That's what our graphs look like. So the temperature in lab A, as time moves forward, it looks like it's increasing. And in lab B, as time moves forward, it looks like our temperature is decreasing. But I want to know what the rate of change is in both places, the rate of temperature change in both places. Well, remember, we had an equation for that before. And yeah, if you remember, it was just y2 minus y1 divided by x2 minus x1, and that's going to equal our rate of change. Here's the problem. You don't have a point anymore. I haven't given you a table of values. You can see where the graphs end, but that doesn't really tell you too much, does it? So you have to find valid points on the graph that you can use with this equation. I'll show you a couple of ways that you can do that. So one thing that you can do is stating your domain and range. You remember we started with that in the linear relations unit a little while back. The domain and range, that's not going to work for every function, but if you're dealing with a linear function, then it will always work. And the reason for that is that a linear function, one end will always be your lowest for both domain and range, and one end will always be your highest. So let's try that with the first example here and see what that looks like. And our domain and range looks like this. The domain, so just the x values, the smallest one is 0. Say on the x-axis I'm at 0. And the biggest value is at 12 on the far end here. I've included all points because every single point, including my extremes at the end, are valid points on this graph. My range, I've figured that out the same way, except this time I'm looking at the y-axis. My smallest value is in between 10 and 0, so that has to be -5. And my greatest value seems to match up with the 10. So that's what I've got over here. Now the reason why this is valuable to us, and again, I have to reiterate, this only works with linear functions. The reason why the domain and range is useful to us is because we've listed all the extreme points, which means that we can now list point on our graph using our extremes. For example, the farthest left on my graph is 0. So my first point is 0. My y-coordinate, so if I'm playing Battleship, what point lines up with 0? Well, there is only one, and we have that value listed in our range. It ends up being -5. That's my first point. My second point is combining my remaining two numbers. So if I use the graph though, because that's probably the smarter way of doing this, I find my furthest point on the other direction, which is 12, and the corresponding point, my y direction, is 10. And now I have enough information to actually solve for my rate of change. And the math ends up looking like this. My delta, my change, is my y2, which was 10, minus -5. So two negatives together make a positive. That gives me 15. And 12 minus 0 is x2 minus x1. That just gives me 12. 15 divided by 12 is 1.25 degrees Celsius per hour. So my temperature in my first graph is increasing 1.25 degrees Celsius per hour. Now, is there another way of doing this? Sure.